that is well worth the expense of doing that to get a faster response. But the point being is that we always have a trade-off that you end up approaching against. Right? Okay, so different access paths. So again, it describes a couple of different ones. We have inverted indexing and fully indexed, and we have secondary indexes, and we have what we call sparse indexes, right? There's all kind of different indexes that we can have. So we'll be talking about the creation of those and how you decide which one that you want to ultimately do. Right? Okay. We also have general purpose versus special purpose. So what we're talking about there is what happens if you just go out and buy or license a database management system for your application. You're going to go out and get probably a very generic one. Okay. Okay. And it's going to work. Well, that's great. Okay. But what comes along with something being very generic? The company is trying to sell this to everyone in every case for every reason. So it's going to be general. So if you have a general application, it is going to work okay. Right? But we also have very special purpose ones, right? So special purpose is literally what it says. I need this database application to access and process this data in this specific way because I have a specific need that this database management system has that other ones don't. And what is going to be the price of a special purpose one versus a general purpose one?
Labor.
It's going to be higher because, right, you are selling less of these, so to get their money back, they have to charge more. But you're also going to fulfill whatever the specific need is. So again, if I can use a general purpose one and it can be potentially not matching the need that I have, so it's going to be slower, but I need something a lot faster, so I need to get the special purpose one if I really want it to meet the needs, but now I have to pay a higher cost. Right? So we always have the things associated with that. Okay, and some of these special purpose ones that we have are this online transaction processing system. So, right, if you want to think of that, this is you are having an online system where you have not a couple of people, but you literally have tens of thousands or more people accessing the system at essentially the same time to do stuff. And it has to manage that. Okay? So, what happens around Thanksgiving? I know none of you participate in this, but right, Black Friday, Black Monday, Cyber Monday, right? Okay. So, what happens on those days related to this? You have a really high transaction volume of lots of people going against this same application, going against the same databases, and what happens if you are the fine owner of this online company and you overwhelm the system with requests because your stuff is so popular, but the site goes down because your database management system can't handle the requests. You're probably not going to be very happy, right? Because are the customers going to stay around and wait for you? Try later, we're having a technical problem. Hold, please. No, they're going to go someplace else. And when you lose that kind of sale, they're not coming back. Right? So, one of the things that we're trying to get to by talking about this is not only do we have to understand the data, but we have to understand how the data is accessed, what are the constraints that you have around it. Right? Now, a lot of times people want to know, well, what's the best it's going to do? You don't really care what the best is. That's just a nice thing to know. It's what is going to be the worst case. Because if I can't satisfy the needs in the worst case, I need to upgrade things or redesign things so it can. So we're always looking at what average case, but what are the possible worst case scenarios that we have to deal with. Right, so what's the worst case in our online world?
Everyone dies.
Everyone. Thanks, Cooper, that's really nice. Good. But our system gets overwhelmed and we can't process. So we have to guess, right? Because do you know what the volume is going to be? No, but you have to guess. So how good is your guess going to be? If it's really bad, your system potentially goes down, or you spend a bunch of money to get this whole big system to handle lots more than what you need to, and all of that is expense. Right? So point is that we have to decide those kinds of things whenever we're dealing with our database systems. So just a real brief history. We've kind of talked about these in general, but just to cover it in a little bit more detail and kind of put them in the sequence. Right? So we'll talk about network, hierarchical, the relational, object-oriented data, and then the object-related models. Right? So the network model was really kind of the first databases to really come into existence, right? So this was in the mid-1960s, right? It was supported by the initial conferences that were dealing with just computers in general at that point in time. So like I said there, it's in the early 1970s, right? And it's related on a bunch of different systems in here that probably most of you have never heard of in terms of companies. Right? But the point is that what's a network? Right? You have a series of nodes or locations, and they can connect to any of the other ones. Okay? So we have that in the way that we look at data, and we can make connections and look at that, but it's really hard to implement that and manage that from a data perspective. So this was the very first one to be created because this really modeled the way that we have data in the real world. But the problem is it's too complex, right? And where are we in the computer science life cycle? We're early on, so you don't have a lot of software to manage things behind the scenes. So the first database management systems were trying to take on something that was too complex to really build, which made it too complex to use. So it was out there, but everybody struggled with it. So the advantage is able to model these complex relationships, represents the semantics or meaning of things, so we had add and delete on those specific relationships. It handled the different situations for modeling, the different types of data that we had in terms of records. So records are just a logical grouping of data. So a student record would be your student ID, your first name, your last name, your address, right? So each one of those are individual fields that we could group together logically into a logical record. Okay. And we had a way to navigate. So, right, if you remember, we talked about two types of languages. We had the data definition language and we had the data manipulation language, which I know that all of you, again, could just instantaneously define and write up and say what it does and all that kind of stuff, right? Yeah, that's what I thought. Okay. So, study, right? All right, so it had its own language, right? So you could find things, right? Okay, and you could literally do your navigation, and you had ways to try to optimize that as part of the process, right? But again, the navigation process is also a disadvantage, right? So we had to do all this processing against very complex structures, right? And so all of these things, and you had internally pointers, so you may or may not have done pointers in your programming classes, but they're real easy to break. And it's really nice that the database management systems manage those for you, but database management systems are nothing but software that somebody has written, and if they don't do it right, your stuff doesn't work, your company relies on it, you have to try and figure out what's going on, right? Again, we're really early in this stage of just trying to get all this stuff together, so it was a big struggle.
I have a question.
Yeah.
In network models, does network refers to the data model, so it's the way that the entities in the database are represented, not where the actual data is stored. Is that correct?
It's actually both.
Okay.
Right? So what they attempted to do, so what Cooper's trying to describe is the fact that we have these things called entities. And if I ask you to describe an entity on the exam, you're to tell me it's a thing, right? It's a logical or physical thing that we're interested in knowing something about. Okay? So from a logical perspective, we have all these things that are all related to each other in some way. So you had to then physically, in the database management system, you had to come up with a way to logically link all these things together from a data standpoint. And then you had to be able to traverse those some way, right? And the issue really turned out to be all this interconnectivity, trying to update it and keep everything in sync at the same time. So when we talk about the hierarchy, what do you know about a hierarchy? You have basically a single parent, so I know I'm going to get there. In a network, I might have 4 or 5 different parents because of the way that the network laid out. So coming in, you could come in all different ways to get to the same place and do different things, and right, it was just too complex to manage. So, Cooper, to answer your question,
Yes.
do you know what you asked me?
Yes.
Okay, just making sure. Because as you're playing your game back there, I don't want you, losing track of.
Writing reviews.
Yeah. Oh, my review? Why, thank you. That's nice. Right? Does a great job. Yeah, just type that every time. All right, so hierarchy. So again, this was kind of the same time, but again, it did follow on to the network one. The good news from the network or the hierarchy perspective, right? This was done by IBM, right? And IBM was a main player in the hardware space at that point in time, and hardware was then, of course, linked to the software that was managed, right? So, right, the idea is that we had the information management system, or IMS systems, and that's still what it's called today. So you can go out to IBM, and you could license a hierarchy database management system called IMS, or Information Management System, and it's based off of what this was based off of, because the structure of it really hasn't changed, right? As we talked about, right, what has changed over time is the speed, right? The ability to access things faster, right? So the query processes, the updating processes, indexing processes, right? So the concepts haven't changed, but the way that they have done it behind the scenes to improve it is what's taking place. So again, if you think about it from what your perspective is, right? if you think about vehicles that you drive or have purchased over the years, they have tended to get better mileage through the years, not because we're still using the gasoline powered engine, but the technology that is behind the scenes driving that allows us to get better efficiency. Right? So it's the same kind of thing. The software is just doing the job for us in the background. Okay, so the IMS product had, and as we said, still has a very large customer base, because again, if we think of data, we can a lot of times put it into a hierarchy structure. Right? So, as I said, right, is I can think of it that I have a part that is produced or sold by my company. I'm going to have it in a certain number of warehouses or a certain number of stores. Each warehouse is going to have locations associated with it that's going to have a certain quantity of this part located in it, right? So we can structure a hierarchy of that data, and the way that it logically does it is it groups all of that logical data into one location in the database. Right? So what takes the most amount of time in running any of your computer systems?
Reading from disk.
Yeah, reading and writing to disk, right? So going out, right? So if you have to go to your hard drive, it's going to be faster than you go to a USB drive, which is going to be faster than going to something on a DVD or a CD or something, right? You typing it in is even slower, especially me when I can like only type with two fingers, right? So, right, a lot of times your software is doing nothing because it's waiting for data or waiting for data to be written out and the acknowledgement that that's happened so then it can continue, right? So one of the things from a hierarchy perspective is it grouped all the data together so that I move data around the computer in big chunks. So in a relational system, you can have all these different relational databases, but they can exist all over in different locations. And because they're all in different locations, to go out and access those and get all the data together typically takes longer, right? So again, we have a trade-off, right, that we talk about. Okay, right? So again, the SAS would be another system that's based on this kind of model as well. So again, some advantages, it's simple, right? So unlike the network one, you only have one parent. You can have multiple children, but there's always one parent. A child can have multiple children, but those will only have one single parent, right? There's operations that's going to allow me to move through the hierarchy with a single request. I can go from the top of the hierarchy to the bottom of the hierarchy, right? So I don't have to access one individual record at a time, right? Okay. So as we said, it corresponds to a number of natural hierarchy organized domains, right? So if you think of a organization chart, right, that we have, right? So companies have organization charts. Do you have that here at school? You have colleges, you have departments, right? Things like that. We have hierarchies there, right? You have hierarchies within buildings. We have all kind of hierarchies all over the place, right? Okay. The language is simple, right? So we have constructs like get. Go get something, right? Get unique. So I want the unique instance of whatever it is I'm looking for. I'm at a location, so get me the next one, right? Whatever the next thing is, go get it. Get the next one within the parent boundary, so get me the next child from where I'm at. Right? So it's very simple to organize and access the data, and so like I said, it's really fast. right? So disadvantages is that we do have navigational and procedural nature of the processing. So we have to now think of it not as relational, but what is the hierarchy that I created and how it's going to work. Yep. Okay. Now they list it as a disadvantage, but I don't really see it as one. But the database is visualized as a linear arrangement of records. Right? So first off, it's not visualized, it actually is stored that way. So it physically stores it in the hierarchy. And because it's written out and stored as a hierarchy, that's going to allow it to be actually faster. So I would actually argue that their database as a linear arrangement of records is actually an advantage, not a disadvantage, as they say it here. Now, if you're looking at it from a person's perspective, you don't really care how it's laid out. So, okay. Okay, there's limited scope for query optimization, and the reason for that is, again, this is a trade-off one, right? Okay. I don't have a lot of optimization because guess what? The data is already optimized in the way I'm storing it. So as long as I keep it organized, the last two are actually advantages. Okay? So where can it be a disadvantage? I have this all laid out and I start inserting data in and it doesn't fit into the nice blocked area where I've organized the rest of the data. So now I put it off in another location. And then another one comes in and I have to put that in another location, right? So now I'm back to, have to do I/O operations all over the database to retrieve the data I want, and it's going to slow it down. So there's always the two favorite words that we have in IT. It depends, right? So if you keep it organized, you keep the structure in place, you define it in your design correctly, this can be way faster than any of the other systems that you have out there. You design it poorly, it's going to react poorly. So I've had some of my IMS systems that literally every week we had to unload all of the data and then rebuild it to put everything in the proper spot because it degraded over the week as we kept adding and deleting things. Right? I had one that I had to do every single night. I had other ones that because we didn't have a lot of adds or deletes in 12 years, I never reorganized it at all. Right? So it's not a one size fits all. You have to understand your data, how the process is against it, monitor how it's going, adjust what you do along the way to make it all work. Okay, relational, right? So relational was first proposed in the early 70s, and its first commercial one was in the 80s. So it's right, a lot of commercial products are out there. So if you look at so IBM has IMS, which is hierarchy. IBM also has DB2, which is relational. So even within the same company, they market different database management systems to different people. Right? So it's up to you to decide. Right? So Oracle or SQL Server, right? We have all these different kinds of things. Right? There's open source implementations of it. Right? And as we said, it's the most dominant for developing database applications today. And the reason for that is it's conceptually really easy to understand. And it matches easier to our data modeling. So the next chapter that we're going to talk about in class is really about creating a data model. So because they match up, everybody goes, oh, it's going to be so much faster to do this. Well, it's only faster if you design it correctly. Okay. So we have the structured query language, right? So we've talked about that a little bit. So there's different versions or iterations of that. But in general, right, you take the structured query language, you can go against any relational database and see what it is. Okay. And because it is so popular, there are a lot of front-end generators, so people literally don't have to understand the structured query language because they're not going to write it, they're just going to point and click on things, right? So if you go to your Microsoft Office and pull up Microsoft Access, you can just point and click on, I want these things, and behind the scenes, it will generate the SQL for you. So you can look at it, you can see what it generated, right? What's the problem with having all these really cool generators?
Right?
No. What's the trade-off?
Get anything outside of the legacy.
Yeah, so, right, it's, they have made it so that anyone can use it. And again, if it's generalized, you get kind of all the extra overhead associated with it, right? And it's going to generate it their way, not necessarily the optimal way, right? So we don't use any generators. No, we can. We don't use any generators because we found that we can code it way better individually than using the generators, or even starting with the generators and making all the modifications to make it all work. And we have to do that because of all the accesses that we have to do. Okay. So in the example that I've given you kind of multiple times, right? So to call the knowledge-based system or inference engine that my team is using from a artificial intelligence point of view or machine learning point of view, I have to go out to over 400 different relational database tables and retrieve that data to send into the system. Well, the generators are not going to be able to optimize my way through over 400 databases to do it effectively. So because of the time, we have to do that kind of stuff ourselves. So that's just an example of the kinds of things that we're doing. Okay, the object-oriented data models, right? So we've had different proposals over time to do that. Okay, we have the idea that we want to integrate those into our object-oriented programming languages like C++, things like that, right? Okay. Smalltalk, I don't know if any of you have ever actually done that, but that's more of a inference engine type of process that rather than a procedural type of language. So the idea here is that we have different types of programming languages accessing these same types of data, but it's all based on this object-oriented types of things. Okay. Okay, so why wouldn't this catch on? What do you think? If you have something that's working, and working okay, being relational, are you going to invest time and effort to move to something that is going to roughly give you the same result? No, right? So we have not had something after relational that has truly been a difference maker. Yeah, we have them and people research things and we're coming up with all kind of different things, but as long as we can make hierarchical and relational faster, nobody's going to take the time to migrate off it. Okay? So kind of to frame it for you, right? If I was to take my application and say, we're going to scrap the hierarchy stuff and the relational stuff and go to object-oriented with no change in functionality. It would probably take my team times 3, so roughly 60 people, probably 3 years to do that with no direct change in result. So companies aren't willing to pay the money to do that. Okay, so it's there, that's nice, but, okay. Right? So the object relational ones tend to mix object models with relational, right? So again, it was, well, let's kind of merge some things together because like, maybe people will want to do that. Right? So relational systems incorporate concepts from object databases to this object relational, right? Okay. So this is kind of behind the scenes. So, right, as we can see in here, we have Oracle, DB2, SQL Server, and other things, right? So they have tried to integrate some of this stuff. So they said, we really like some of these features, but we're not going to go full-blown object-oriented, but we will integrate the pieces in because we, in general, use a lot of object-oriented languages. So whether it's C++ or Java, right, Python, the Visual Basic, all these kinds of things, they all are based off of objects. So if I can use some additional things like that, right, there's even relational versions of COBOL, which, oh, that's old and ancient, but there's billions of lines of code out there, right? To rewrite all that is just a huge cost. Right? So, if you want a job making a lot of money, ancient technology is where it's at. Absolutely. All right, so object relational is kind of disappearing because, again, it's being integrated into the relational models that we have today. All right? Yes, sir.
What happens if you combine hierarchical with relational?
You can't.
Why?
Why? Because the concept of, there are different concepts in general, right? So if I actually, in a sense, in relational, I can create hierarchies. We don't call them hierarchies, but they literally are, right? But they want to keep them separate from the standpoint of just terminology. Right? So you can create those structures, you can access those in hierarchy type of structures, right? But the difference is going to be that the way that data is physically stored and the way that you access it behind the scenes, they are two completely, if I look at the way that the data is physically stored. I can logically make an argument that they are the same, right? Because if I have that parent being the part and the warehouse being a child, that's a relationship. So I have a relational database that I could create out of that.
But you can't make use of the speed of that model.
Right.
Yeah, okay.
Yeah. So it's the behind the scenes thing is not good for combining. But from a stand back and look at it, I can say they are both the same because I identify all the relationships that we have and we are building those in. So, in a sense, they have done that, but from a terminology standpoint, we keep them separate. Okay, so to answer your question, review did a great job. Type it in right now. All right, so the next thing that I want to talk about is this. So we talked about the fact that we have data dictionaries. So in the last slide set, part of that was about that we have active and passive data dictionaries, right? So we have active ones where the database management system is involved in using it, and we have the passive ones where it's the users and the DBAs that are dealing with that. Right? So this is an example of, so my undergraduate class, so this is an example of the database or data dictionary that they had to create in their class. So I had them actually create one. So the data dictionary is not something that automatically comes with a database management system. It can be separate, it can be integrated with that, right? But the idea or the concept that we have associated with this is any piece of data that you're going to have has a definition associated with it. And if we're going to do this effectively from a computer science point of view, we have to know what that data is and where it's used and how it's used. Okay? So if we look at this one, and again, this is just the high-level overview of this, right? So if you look down at the bottom, we have a number of different tabs. So we have actors, which are kind of the users of the system. We have the individual data elements, so those are the attributes that you have. We have data flows, so this is flows not necessarily the between databases or anything like this, so this is at a kind of application level. Right? Okay. We have data stores, which is your databases or files, things like that, so it could be any data store. Our external entities, so who is integrating with it that's external to the system that we're in. And what we're seeing on this page is the processes, right? So there's lots and lots of different data dictionary software packages that are out there. And a lot of companies don't like the ones that are out there, so they create their own, right? Because how are you going to use this and what's the right? So this is just a simple Excel spreadsheet to help us manage things, right? And right, so it's not very complicated, but if you look here under processes, we have the name. We have a one-sentence description of what the process is that we have. Who is it, or what is using it? Right? So, right? And then what are the data flows that are going to be included or interacting with this particular process? Right? Now, in something that is more technical than just a spreadsheet like this, right? So in our example, I could, for example, anything that is already defined somewhere in the dictionary, I could click on that and it's going to bring up that entry. And in that one, I could click on something and bring, right? So I can link all these things together. I didn't ask them to do that in here, but that's how in real life we end up being able to trace things through and find out what all the definitions are. Right? Okay, so if I'm looking at the data elements, right? So I have this was what is the name, what's the description, again, who's using it, right? So this was a warehousing distribution center, right? Minimum, maximum values you can have, what is the units that are associated with this, if there is one, things like that, right? And right, this is only a small fraction of the number of pieces of data that you would have associated with the data elements. Other ones that you would have are the data types, right? A lot of ones expect examples of what it's going to be, what business terms are associated with this, right? So this is, again, it was more to give them an idea and you to have an idea of the types of things that we do and how we link them together. Right? So in the data stores, we have the data stores, the description, and who it's used, and the data items that we happen to be storing in each one of those. Okay? So again, we had, what's our T word that we're going to have to remember on the exam? Traceability, right? I should be able to look on a data store, and if it says this is an item that is stored in it, I better find that particular data item in the data element list. Okay? If I say that I'm going to be storing a data record, I better find that data record in the data record category, and the data elements that are in the data record, I better find in the data elements one, right? Everything has to tie somewhere in here, right? Okay, and that's getting back to kind of Cooper's idea of when he went to find his account and why I have to spend roughly $300,000 a year is to make sure this is all updated correctly. Because you have to tie everything together. Right? Good news is once you have this, you only have to do it once. Yeah.
Is traceability a design principle of data dictionaries, of the database as a whole? What does it apply to? What's its range?
Everything. Literally. Right?
Sure, in the context of this class.
In the context of this class, everything in this class. Right? So if I have, and we'll just run through the scenario that we have, right? So in general, if I'm going to use databases, they are typically going to be used in some sort of application or in some, to solve some kind of problem. So I need someone to define the problem. If you can't tell me what the problem is, I am not going to be able to give you a database that's going to solve the problem. Right? So there should be a problem statement. Right? So in general, when we are building an application, right, the problem statement is probably like half a page. Right? This isn't a dissertation. You're describing what is the correct problem you are solving. And what happens if I don't state the correct problem?
Solve the wrong one?
I solve the wrong one, and we solve the wrong one a lot. Okay. So, what should be your first traceability step is, I have a problem statement. Is this the correct problem I need to solve or not?
Write it down.
Well, you write it down and then you review it and you say, is this really going to solve? Because a lot of times what we end up doing is we solve symptoms of a problem. And then we find out, oh, we solved the symptom, but we didn't solve the problem. So now we have to do the project again, but we didn't really do our due diligence and we solved another symptom of a problem, right? So we end up doing 4 or 5 iterations to finally get to what we could have done the first time if we really thought about it. Okay, so now I have the problem statement. Now, someone has to say, that's great, you know what the problem is, but now what needs to be done, logically, what needs to be done to solve that problem? So what are all the steps? Right? Okay, so typically it's the person that is describing the problem is going to say, here are the steps of what I want you to do, right? You being the company. What do you need to do? If you follow these steps, we are going to solve the problem. So what do you have to do at the end of that step? I'm tracing what all these steps back and say, based on the problem statement that was given, does these steps solve that problem? If the answer is no, you have to update it. If it's yes, I can move on. If it's got extra stuff, you say, do you really need to do those things? Because that doesn't match what the problem is. So is the problem wrong? Okay? So then you move on to analyzing these steps to solve the problem. And you say, can I take what needs to be done there and solve it from a technology perspective. Right? So this is where you're now looking and saying, what kind of data am I going to need to do that? And I need to put it someplace. So what database management system would I use? What are the pieces of data? Is it defined correctly? Do I even have access to that data? Does it exist today? Right? So you're going through and saying, is it technically feasible to do that? And the next step of what we are going to be talking about is part of that process. So great segue there, Cooper. Right? So the next step is figuring kind of that stuff out. I'll get to you in a second. Right? So once you know that you can do it, then we have to design it in detail. So we go from a logical view of the databases and the programs and actions around that to a detailed. What is physically going to be on the database? What kind of indexes am I going to need? Is it going to be fast enough, right? And I'm tracing all of the actions all the way through till you build it, you test it to verify it, you deploy it, I have to maintain it, right? And each one of those you're tracing all the way through the process. So I should be able to start anywhere. I can start with the analysis and work to my detailed design or back to the specifications, and everything should match. I should be able to go to the specifications and go back to the problem statement and go forward to the analysis. The detailed design, I should be able to go back to the analysis and go forward to the testing, right? Everything is traceable. So when I say everything, it's literally everything. So, she's next. Yes.
So when you're tracing through it, if you can go back all the way around, like, does it matter? How are you organizing through it? Because you're saying you can go from like the design to like anywhere.
Well, in general, your projects are always progressing from problem statement forward, right? But you also know that change is inevitable, as Mark would say, right? And as you make changes, you need to go backwards to make sure that you've understood what that change is and how it fits in, and is it truly the change that you need to make, right? So for us, right, when my team does it, and they hated this at first, right, is we literally get in a room like this, and we have 3 screens, and we bring up the different artifacts, and we pick the lead artifact and highlight a piece of it, and I should find it in the other 2. And at the end of the lead one, all the others should be completely highlighted as well. They never are. Right? Because by that time, we found that one of the other ones is missing something. And then you have the discussion, well, why is it in this one and not in the other ones? And sometimes you don't need it, so you end up deleting it. Or you have to say, oh, well, this is a change that happened at this point, and we need to go back and update the prior one. Right? So I've had instances like that. But in the end, all of the artifacts that are generated out of building all of this should match. And yes, it takes a lot of time, and that's why my team didn't want to do that. But in the end, because it all matches, going off and actually building it was way simpler and way faster. Why? Because in our database example, I didn't say, okay, team, go out and make this database. So I go to the data administrators and the database administrators, and they build this, and then I come back 2 weeks later, oh, I need a couple new fields. Can you add those? 3 weeks later, oh, I need a whole new database added into the mix. We didn't think about, right? They get They don't got time for that, and we don't have time for that. We need to define it correctly up front. And it takes work to do that, but in the end, all the work gets done faster. And it took me about 6 years to get them to realize that. So it's really tying that all together. Right? And again, once I have all the data laid out in my data dictionary, it's only updates to it that I have to do. It was that initial investment that was huge in terms of time and effort. And nobody wanted to do it, but I finally convinced them to do it. And now, like I said, I'm doing $300,000 to maintain it, but it would probably cost me $1 million to do the work that I'm saving. If I was to map it. Right? Because it's built once, and once it's there, it's typically doesn't change. Now, where it's used and stuff like that changes, but the definition, and because I have a data name, the data element is named X. When it's in the data record, it's named X. If it's in a program, it's named X. Right? It's consistent, so no matter where you are looking at it, whether it's the database, the programs, anything, X always means exactly the same thing. So I had a situation where I had a sequence of programs, and every single program done by a different person, and they all named that same field something completely different, and it was named differently on the database. So every time we went and made a change to that, everybody had to always figure out, is this the exact same thing or not, because it's named differently. Well, that's okay if you're doing one field, but we're doing 1,000, 2,000 fields. Right? So you gain it back pretty fast, but nobody wants to put in the initial investment because there's no benefit in their mind when there's actually a huge payoff. But somebody's got to pay for it, and nobody wants to be the first one to pay for it. So, did I answer your question? Okay. So, Cooper, you had another one.
Yeah, I thought I heard the answer already.
That's great.
Yeah.
He answered the question before I even asked it. Put that down on your.
So, would you say we need to be able to trace everything all the way back to the problem statement?
Because at the end, when you say, I'm done, your goal is to go back to the customer and say, okay, sign off because I have solved your problem. And if they can't do that, then somewhere between them defining what it is that you are solving and what you delivered, there's a problem. And then, because they typically go, there's just something wrong about this, right? It can take weeks, months, sometimes to figure out what the problem is. And then, of course, all your stuff doesn't match anymore. So the only thing that you can trust is the actual code in the program and the metadata that you have in the database. And I don't want to be stuck in that situation. So that's just too much work. Right? So, again, the point of this is that I want you to see, just kind of in general, that every piece of data that we have, everything that we deal with, has a definition. And what do we say one of the first jobs you have when you move anywhere within a company or you go to a new company? Figure out the data and the processes. Because how can you be successful if you don't understand what that is? You go, you have a data dictionary? No. Well, what data do you use? Well, here's a few pieces of data. Yeah, but how many pieces of data do you have total? Oh, well, I told you about 10 and we have 60,000. Okay. Well, who can tell me about the 60,000? Well, there's not really anybody that knows all of them. Well, then how do you get anything done? Well, we have to go to Mark for this, we have to go to Cooper for that, and right, there's, well, Mark's not here this week. Well, I guess we can't do anything on it until Mark comes back and he can answer the question, what this piece of data means. Right? We can't be caught like that. Right? We have too much work to do. So, okay, any questions on this? So again, it was more just a give you a sense of the kind of things that we have to do. And again, your true database management systems have a lot more reconciliation between all of these than what we're showing here. This is just to give you a concept of that. Okay. All right, so data modeling. So we are specifically doing data modeling in here, but in the concept that we just talked about, that was that nice, wonderful segue that Cooper brought in for us, right? We do lots of different modeling related to what we're going to end up building. Okay? So in that description where we said, what is the most important thing that has to happen in all those steps that we laid out?
Traceable.
No, that's how you know it's right. But what's the most important step?
Repeating it back.
What's the first step? Define the problem, right? If you don't define the right problem, right? Cooper, this is what gets me about Cooper, right? He gives me the answer, right? I ask him to repeat the answer he gave me, and he strays off, right? It's crazy. Can't think, right? If we don't get the problem statement right, we are going to be doing the wrong thing all the way through, including our databases. Okay. So once I have the problem statement, I have to figure out what are those steps. The steps are defined in what we call scenario modeling. So scenario modeling is what is the scenario or usage of what you're going to see. So what's the series of steps that we expect to happen? Right? Now that's really important because of what? If I don't know what steps need to be done, I can't tell you what data that you need to do those steps. And I don't want to figure out the data and the steps unless I know the steps are correct and actually solve the problem. And going through that process going forward and backward is the traceability that we are talking about. Okay? So when someone tells you from a scenario, I want a screen that has this data on it, what's your job? I have to know whether I have that data, where I can get that data. Does that data exist today? Doesn't it exist? Things like that, right? And what happens if it doesn't exist? You have to figure out how you're going to get it if you're going to solve that problem. If it already exists, you say, great. Right? So when I get a set of steps like that and I look at it and I say, oh, this data is already on database A, that's less work for me because it already exists. If I go, it doesn't exist, so I'm going to have to make database L, now my workload is now increased. Right? So we are always asked, how much effort is it going to take to do this? How much time is it going to take? All that stuff. Well, that's one way that we have to go through to estimate it. Right? So we have scenario modeling. We have behavioral modeling, which is states. And what do we mean by a state? A state is what is the current set of data values that you have in your record. So a behavioral state of a database is, for example, today, here in school, you have a student record, as we said. It should reflect your student ID, your current name, your current address, your current phone number, all those kinds of things, right? And what happens if you move partway through the semester? We have a change of state, or we change of behavior, because we're changing your old address to the new address, right? So we have behavioral or state changes. Okay? We have in your programs, we have the concept of those objects, right? So you have classes, you guys have all coded that, right? So classes have data, the actions on that data, right? That whole abstraction stuff that Mark knows so well, right? Data and procedural, encapsulation, information hiding, right? All those kinds of things, right? So we have our classes, and there's 3 types of classes that we deal with. There is the boundary classes, right? So interfaces, right? Somebody's on a screen, right? We have entity classes, right? So student, textbook, course, right? And we have control classes, which are the processes. Now the important one is, for us, in this class, is entities. Because typically, entities are the things that we're interested in that we need to keep data about, which translates into databases. So we are concerned with classes and what should match if we do traceability. The definition of a class that appears in a program that's related to a student should match to all of the data that you have on the student database. Shocking. Right? So again, traceability will make sure that you have so if I add a piece of data into the class in the program, it should appear on the database, and if it's not, there needs to be a justification why. Because they should match. Right? And it could be, well, we just don't need to store that, because we'll never reference it outside of the class. It's something we calculate. Okay. So we have derived data that's related to a student, for example, that we don't physically store on a database. That's okay, right? But at least you've thought about it. And where should it be documented?
Data dictionary.
The data dictionary, right? We did not include this in the database because, right? I can't tell you that I was, like I said, I was in the same position on the same application for 17 years, which was really beneficial for me and my team, right? But my business customer, one of these sets of them, changed about every 2 years. And everyone that took on that position had the exact same question at some point. So what would I do every single time? I would go out to the data dictionary. I would copy the entry that was out there. I would put it into the email and I would say, send. And it answered that question every time as to why we didn't do something. But everybody had the same question. But they would never look it up because, well, that's like really hard. I'm going to ask somebody. Well, what if I had to look that up every single time? Right? I knew it existed because I was part of the decision-making process as to why we didn't do that action. So when I moved, what happened? My wonderful peer that took over for me and the new customer, they asked them, and of course, they were able to do what? go to the data dictionary, look it up, copy the same thing. So did it save them any time? Yeah, because they didn't have, and it saved me time because they didn't have to come ask me. So selfishly, it helped me out. Okay. So we do class modeling, we do data modeling that we're going to be talking about here, we do behavioral modeling, we do scenario modeling, we do process modeling. Right? So what is the sequence of actions that are going to take place? Who is going to do those? Right? And what is the specific sequence and what is the starting point and the ending point? So those also tie back to our scenarios, right? So again, all of these different models end up having to tie together. And how do we tie them together? Traceability, right? And what happens if they don't match? Different people use the different models to go and create their own part of the thing that they're building. And what happens if they don't match? The end result is you have something that doesn't work because it doesn't match. And then what do? You argue about who's going to make a change. Because nobody wants to make a change because you're already behind schedule. Right? So we get into all of these things and waste a lot of time. So all that traceability up front, all the different types of modeling that we do, and get it right before you, right? You're never going to get it completely right either, right? So we can drop into that whole analysis paralysis thing where you're trying to get it absolutely 100%. You can't do that either, right? It's, you get it really close and move on, right? You know changes are going to happen. You're going to have to go back and make adjustments, but you can't wait forever. All right, so data modeling, and we're going to talk about it in terms of the entity relationship model, or specifically the entity relationship diagram. Right. So my starting point with this is entity is what? A thing. Right? And these things have relationships. And we're going to diagram those. Excellent, right? So we're going to create an entity relationship diagram. Okay. Now, I am also going to tell you that what they talk about in most database classes, what they do at most companies, and what you will typically experience when you get out of here is the wrong way to do it. But the good news is I'm going to tell you the right way. Okay? But unfortunately for you, the company that you're going to work for will not do it the right way, and you will not be able to convince them to do it the right way. But at least you will know. Right?
Are you
So-
also teaching the wrong way?
Huh?
Are you gonna also teach us the wrong way?
No. No, because the wrong way is a subset of the right way. Okay. So, okay, people tend to think of the entity relationship specifically in terms of databases. So this is where we fall into the trap. Right? Entity relationship is everywhere, and you can apply it in any situation. Okay? So, what is a model? Let's start with that.
Useful abstraction of reality.
Yeah, it's a abstraction of it, right? It's a model. It's a representation of something. All right, so if we were to talk about, in which we've already talked about in here, we've talked about the idea of campus and the things on campus. Right? So, what do we say are the things on campus? We have you as a student. You have me as faculty. You have what you're taking as a course. This course has a textbook. You get to pay tuition, so you have an account, right? You are taking courses that were developed by a department or offered by a department. The department is within a college. The college, a group of colleges make up the university, right? Okay? The classes that you take are located in a building and they are on a schedule that have a section. Right? Right? And what do we also have on campus? We have other employees and staff. We have different types of students. We have graduate students like you, we have undergraduate students, we have guest students, right? Okay, so that's just like off the top of your head, we can list off a whole bunch of things that are here. Okay? And we have computer systems that generate all this stuff. Right? You walk over to the CIS department and they want to show you information about you as a student. They can type in your student number and on the screen comes up a nice representation of you, and it's got your ID number and your name and address and all that kind of stuff, right? And if we want to see a representation of your account, you can go in online and look and say, look, I have paid the university more money, so I have a negative balance in my account because I've paid them extra. Guess not. Right? So, right? And what is the schedule for this semester? Right? You can go out and look, and there's the schedule of classes that are up, right? I mean, we generate all these things by some computer systems. Okay? Okay, so what is at the end of the road here? The environmental area, right? Okay, is that a system? It's not a computer system, but it's a system. Does it have things? And are these things related? I have plants, I have animals, right? We have, right? So I could model the environmental area just like I can model the school. We can model economic things, right? So there's all kind of models that we can create, right? So entity relationship, the first mistake that we have is that people only think of it in terms of this is a computer system. And these are the things we're dealing with here. Okay. So the idea that we want to get across to you is that if we're going to model something, right, we're modeling the system that we have. So it could be a business, it could be an organization, it could be part of an organization, it could be a system like the environmental system, right? It's, you are modeling something. Okay, so that's a good start, but what do we end up doing, right, is when we tend to build entity relationship models, we build them only in terms of the databases. And we do it as part of our projects. Okay. So, what could be the problem with that? So that's the wrong way, right? Is we build these models and they are very specific to the project. How's it, yeah, right? If I only have my view of this right now for this particular project, I don't know how it ties into the whole picture. And I didn't even pay Mark to say that, so thank you, Mark. Okay, so it's important, if we're going to do this correctly, that we have a entity relationship model that represents the complete picture of what we are going to be looking at. Not just the project perspective, but the complete picture. And I've given this thing a really great name. It's the complete ERD. Is that pretty clever? Huh? I knew you guys would like that. Right? So we want a complete picture, because what is the complete picture going to give us? What are all the possibilities? What data do you have available to you? What relationships exist? Not what did you build, not as what's currently there, but what is possible. Okay? And I will tell you, because I've created the complete one for my part of the organization, right? And I have reviewed that with my business customer. And they're like, I didn't know we had that. I didn't know we could do that. Because if I only showed them what we actually built, they wouldn't know what's possible. And what else happens if I do all these individual pieces? How do I know that I didn't change something? Okay? So I've had instances where I have worked with teams where they ended up having in one case, 4 different versions of basically the same thing, because each team within their same group came up with a different layout of what it was going to be, didn't call it the exact same thing, and ended up creating and building 4 separate instances of the same thing that now they had to struggle to keep all of the data in sync because it had the same data across 4 things, and so now you have all this replication. If you changed it in one, you had to make sure it changed in all the other ones. So they complicated their world immensely because they didn't take the time to do it right. So, understanding the big picture, being able to combine it in ways so that you understand what you have, what's possible, and this also then helps you say, oh, you want this problem solved, I can go to the model and say, do I have all this data? I know what I have built, and I know what is possible, and that helps me estimate the work I have to do, right? So, just like I named the big picture one, the complete ERD, the one that we typically talk about in all your database classes and the ones that you will do when you go work someplace, I have named not just the ERD, but the build ERD, because that is what we have actually built. So we have a complete and a build. And you need to understand both if you're going to be completely successful. So why would we not create a build? Because how many times would you have to build it? Once, because it represents the entire organization that you are working with. So why don't we build it? Create the whole complete one. It takes time, effort, right? And who's going to pay for it? Not me. I can't do that because I have to get my project done. Right? So, so I was lucky enough in one of my jobs that the company that I was at actually created one. And just to do our section of the company that they were doing this on, just to kind of give you a perspective, they had 4 people working on it full time. It took them 6 months to create it. Right? And because what do they have to do? They have to go interview everybody in the company to come up with what are all the things, what are all the relationships, what are all the pieces of data, go back and verify everything. Oh wait, what Mark told me is different what Cooper told me, so I gotta figure out what's the real story, because it's probably not either one of theirs, it's some combination, because they're all coming at different views of it, right? But I will also tell you when they created it, and they created it close to 25 years ago, it is still in existence today. They created it once, and they have used it continually since. And I can't tell you, because I was there for 12 years, part of that was developed in it, but the 8 years that I had access to that, it saved me a bunch of time. Because I already knew what was there. Right? So, complete and build. Complete should show everything that is possible. You have to do it once. It applies to everything that you are going to do in the future, and it relates to a database because the entities that are on here, if you are going to use them, you typically are going to turn those into databases. So knowing which ones are there, that you've built, haven't built, what attributes you have, all play into what you end up actually using. Okay.
But just a question, when you say complete the relationship, so that's till the completion of the project, is that what you call it, or completion of the application?
No, when we talk about a complete ERD, you are modeling something, right? Okay, so if I'm modeling something, right? So let's give an example. Okay? So let's go back to the school scenario. Right? So given all the things that I listed earlier, right? If you were to create a schedule of courses that are going to be offered in a given semester, what are you going to need entity-wise to do that?
Classes,
Right, so courses, right?
instructors,
Instructors, so faculty,
students,
no? Do students appear in the catalog or schedule of classes? No, right? So buildings,
yeah, classrooms.
right? Well, time is, right, I don't have a database of times, or we actually can if we have we have blocks that you can offer things in, so you verify that, right, so that's maybe. Right? It's what? Right, so not only buildings, but it could, we have the rooms associated with those. Courses. Right? So, point is that we have that set,
Right.
right?
Okay.
But what didn't we mention? We didn't mention students, we didn't mention other employees other than faculty,
Right.
right? We had course numbers, but we didn't have necessarily a department, right? We didn't, right? So, point is that if the only thing I concentrated on was the schedule itself, because that's what I'm going to build, how does it fit into the big picture of everything at the university? Because I've excluded looking at these other things, which is okay for what I have to build, but what if I now want to include something that I didn't originally? Right? If I can look at a model and say, oh, right, you want to add this additional feature into the schedule, and I can get it from here, then it's going to save me time, right? And if I only look at my build ERD and some other group has built what I already wanted, but I didn't know that they built it, I may build it again. Do I really want to spend the time to do that? No, because somebody else has already created it. right? So if I have so what I do, right, is I have a complete ERD. Right? So it represents everything that I know about my piece of the organization. Every project has a build ERD, which is a subset of that. And I go back to my bill or my complete, and I change the color of it to say, I have built this. Right? So in the first project, I may have built 5 of the 27 things. And then the next project, I used 7. 5 were already there, and I added 2 more, so I highlight the additional 2. So I always know from a big picture perspective what's possible, what I have actually already built, and then for any given project, I can look and say, what are the individual pieces did I actually use out of everything that was built in this particular project?
So in this particular instance, we are talking about a college system or university application. But let's say we fast forward it and we come to a conclusion, or we come to a point where the project is we have built all of that.
Mhm.
Now, then later point there is some bigger changes happening, so then we have to add on to the complete TRD, right? Again, complete TRD.
Right, but in general, your complete is going to rarely change because it represents everything that is possible, whether you have built it or
So
not.
you mean in the scenario, you have to think about, okay, what about acquisitions, mergers, splitting,
Yeah.
divestiture?
Yeah, I mean,
all that?
it's not that it's never going to change, and there's going to be reasons it does change, but it is going to be rarely changed compared to all the projects that are coming up. Right? But again, I know, looking at the complete, what is it that's possible? And then if it's not there, I know that it's a bigger change because I'm gonna have to go figure out where this is, where is this data going to be coming from, right? Because it doesn't exist in the organization today, anywhere. So that's gonna be a bigger effort, right? And if I say, oh, it exists, right, we just don't capture it, I know that I have work to do, but the data actually is there. There's no process change that has to do that. I just have to figure out what process is going to generate that data that I'm then going to use to solve the current problem, right? And if I look at it and it's already built, then I don't have any data work to do.
Right. And this complete ERD will do it well ahead of any systems development.
Yeah, so again, the complete should be completely independent of any project, right? Because you're just looking at saying, for the company or organization that you are modeling, what's the model look like? I'm not solving a problem. I'm saying, what is the data and what are all the relationships that we have?
Right. Even though data doesn't exist, no systems exist, nothing exists.
Well, the data is there, you just aren't capturing it and storing it someplace,
Okay.
right?
Okay.
Right? But if we look at the environmental area, we have animals. The animals exist. I don't have a database that's got them in it, but if I wanted to write on a sheet of paper, an Excel spreadsheet or something, what are the attributes I could have about the animals that exist in the environmental area, right? We think that's so you're heading down the path that we just talked about, right? We are concentrating so much on the system and the application that we lose track of what are we trying to do from a big picture perspective. Right? And so don't feel bad because everybody does that, right?
Yeah.
Because that's what we're trying to solve a problem, right? But complete should always be done. It's done before anybody proposes a project, and it's representing everything that is possible in this scenario. Yes, Cooper?
In the case that there's no such thing as a complete, as I imagine is the case most times in real life, is there something that's in between a project diagram and its existence inside of the larger ecosystem? Is there some sort of way to balance the trade-offs of time and complexity versus the needs of the project?
Great question. And the answer is sort of. And it is typically in somebody's head, but it's not written down. And you'll say, okay, let's go ask Mark, because he'll know what the data is and where it resides.
But there's no like way to model it where you're like, there's just an homage to a piece of the business we don't have modeled or built yet.
No, nobody does that because you're
That's
so,
crazy.
well, it's, but again, that would mean somebody has to do work, right? And everybody's so concentrated, kind of to his questioning, right? They're so focused on getting this one problem solved, and then guess what? There's 6 other problems to work on after this. You get the thing done, and you just throw it out of the way, and you're on to the next thing. And we don't tie them all together. And like I said, I've had instances where applications I've interacted with, I have to say, I know you have 4 versions of this thing. Which one should I be accessing? Because I don't know. It makes no sense, right? They've, like I said, they generated so much extra work for themselves, but they're not willing to back off on it because they've invested so much into it.
One more question.
Sure.
So, and I'm thinking about it for an evolving business. You don't even know all the players or how it's going to evolve. In that respect, in that time,
Okay, so you have to remember, right, your model represents a point in time, right? So like we said, it's going to change over time, right? So if I merge with another company, right, I add, right, a new type of functionality into the company, sure, it's going to change because it's, right, it's an evolving, but it should always represent the current state.
Okay.
Right? Right? A complete ERD from 8 years ago is going to be helpful, but things will probably have changed. And now I have to research what is still possible now. Right? So it's how do you keep it up to date? Because it's work. And again, companies don't want to commit to that because they don't see a value to it when there's tremendous value to it.
And that also means that so your involvement should be at the very top for the company to have that sort of a vision.
Yes, so, right, so that's why I was really lucky at that one company that did it. The people at the top understood and they said, right, and they actually got pushback, right? Why are you gonna spend so much money on this? Because in the long run, it is going, here's all the benefits. And I think they probably, I'm guessing, because I wasn't obviously involved in any of that, but I'm sure they argued about that for months, if not years, till they finally committed the funds to do that. Because, right, well, we could spend that money on something else and get, well, this is gonna save you so much time later on in all these other projects that you're gonna be able to get your money back over and over again. Right? So again, it's long-term strategy versus short-term, right? And again, companies overall tend not to have a very good long-term data strategy. We're very good at creating very short-term, project-oriented strategies for data, but long-term or company-wide, don't do very well. And again, size of the company really doesn't matter either. So like I said, where I was the only IT person in the company, they had a horrible data strategy. When I got there, I had to literally figure out everything. Because nothing was written down, right? The person I replaced, right, all their knowledge was in their head. Okay. Oh, we need to update this because Blue Cross is changing the file that they're sending in, and we store it on a database. Well, what database? I don't know. Well, let me look in the program. So what's the file that comes in? I don't know. What do you do with it when it comes in? I don't know. Right? So I literally spent weeks just trying to figure out what their structure was, because they didn't have a overall strategy. Okay? And I'm like, you got to get your act together, right? So it's going to cost you this much. And you're like, oh, we're not going to spend that kind of. Well, did you just see how much time and effort it took me to do that one change? Do you want that on every single change going forward? Well, no. Well, then you got to cough up the money up front. Right? So you have to, I mean, it's an argument all the way through because nobody has a long-term vision. You know? All right, so the right way to do it is to have this complete ERD available before you start looking at any problem to solve. And then, when you get to the database design process, when we are talking about it in terms of internally in the application, you know that it's really highly likely that it's going to be a subset of what you've defined in the complete ERD, and you already know what you have built. Right? So, our two main activities in terms of database process design is around database design and application design. So the focus of what we're talking about here is on conceptual database design. What do we mean by conceptual? What's it going to look like? We haven't physically created it. We don't have an application that's writing data into it or retrieving data from it. Right? We're looking to create the schema that's going to go into where? Where do we store all the schemas?
Catalog.
In the catalog, or what's the other word for the catalog? Metadata, right? So whatever way that I stated on the exam, right? You know that they're the same, right?
Sure.
Well, you better if you want to answer it correctly. Right? Okay, so application design is focused on the programs and the interfaces that access the database, right? Be part of the software engineering process, right? So it's great to look at the program and interfaces, but ultimately the data needs to be there for the programs to either input into the database or retrieve from it or update it on the database itself. Okay, right? So if we look at this wonderful process here, okay, we have our mini world at the top. And what's the mini world? That's the section of the company that we are dealing with, right? And you come down and we have, the assumption is that we have our problem statement already done, right? So the requirements collection and analysis is that piece that occurs after we get the problem definition, right? So we are doing scenario modeling at that point. What needs to be done to solve the problem? Okay. And we break it up into two pieces. We have functional, right? And what's functional about? What functionality do the programs need to perform? The user needs to be able to select from a list of classes which ones they would like to register for. Based on the ones that they selected, you need to go back to the classes that they have taken and verify all of the prerequisites are met. You're going to look to say, right, are any times conflicting because we want to show a message that there is a conflict. We are not going to allow them unless they get an override to do this. We have to look at their account. If their account is on hold, they can't, right, there's a whole set of functionality that would be taking place. Okay. So ultimately, that's going to have to be defined. On the conceptual side, you're looking at, to do all the stuff that's being defined on the functional side, what data do you need to perform that, all that functionality? Okay. So again, what kind of work is this? We're tracing our list of, here is the functionality, here's the data I need to perform each of that piece of functionality. Do I have it? Yes, no. Kinds of things, right? So that's that traceability stuff that we're talking about. Right? Okay. And if I don't already have it built, I need to decide how it's actually going to look, where I'm going to get it from, how I'm going to store it. Is it going to be updated, right? So all those kinds of things, right? So on the left-hand side, we have the transaction specification. So what are the functionalities of these programs? And on the right-hand side, we have the conceptual schema of what our data is going to look like. So where, on this conceptual side, would I be able to see whether the data exists or not, if I had it? The complete ERD would tell us, right? Does the data exist? If it does exist, has it already been built somewhere in some way? If not, but the data is available, I can get it, but I have to create a schema associated with it. If it doesn't exist anywhere, I gotta go figure out a whole process of how to get that data. All right. So everything above the line that's appearing here where the logical mapping, so we see that the database management system independent is up, right? So thinking about the data, the conceptual way it's going to look, all of that is independent of your database management system. Right? So when we do the logical design, what are you doing? You're mapping it to say, here's the data I want, here's the way that it's going to be used, because I know that from the functional side, and then that's where you're making the decisions on saying, what would be the best type of database to use? Am I going to need indexes for performance things, right? Okay, what kind of access do I need, right? So all of that is going to then drive us on the lower half into the database management specific stuff, because ultimately when we get to the physical design, we then have to ultimately build it. Right, so that it goes into the catalog. So the programs on the right-hand side can use it. Okay, so there are two things in this nice diagram that they have in the textbook that are missing. So we've talked about one of those. So which is the missing piece that we just talked about? And where would it go? Hint, it's at the very top.
This thing, I mean, the problem.
Nope. No, that's missing too, so I'll give you that. So there's three then. Okay, so that appears in between the mini world and the requirements collection is problem definition, but there's something before that.
Oh, is it a complete ERD?
Excellent!
Yeah.
Yeah! Yeah, Cooper stuff, yeah. Right? So, mini world is what we are looking at. The complete ERD should be under that because that represents the model of what the mini world that we are concerned with in its entirety, all the possibilities look like. Once I know all of the possibilities, then I overlay on top of that a whole series of problems that we're solving. Out of this, we pick the one that we're going to work on, and then out of that we go get our requirements, right? and our analysis. Okay, does that make sense? So, you were correct, so thank you for correcting me, right? So the two things between mini world and requirements gathering box is complete ERD first, problem definition second. Right. So the other piece we haven't talked about, but it plays an important part in this. And what are the two pieces we have here? We have functionality and data. Okay. There is a third thing at that level. Any guesses?
Relationships?
Nope.
Users,
Okay.
entities,
It's what?
entities.
Nope. All right. So it's non-functional requirements or non-functional analysis. Okay? So what is functional analysis? It's about analyzing the functionality that you expect to be done. Here is the scenarios that we are going to need to satisfy. Right? And we talked about that. That's a series of steps. The student is going to do this, the system is going to do this. In the end, this is what's displayed back to the student, all that stuff, right? So there's a series of steps. What is non-functional analysis? Non-functional analysis is about, you know, performance. That's an example. Okay? Okay, so non-functional is about constraints. Okay? So the example that she just gave was performance. That's got nothing to do with functionality. It's, in this case, if we're talking about performance, it's the speed at which you're doing something. Okay? And why is that important to know in this? Because I may have to design my database for speed. If I need to know what that speed limit is, I may have to design my database differently to do that. So, as an example, my requirement, right, so my requirement is if someone is using my application on one of the screens, from the time that they hit submit, I have 1.5 seconds to get a response back to that user 95% of the time. That is my agreement with my business customer. So every time that I make a change to the system, I have to evaluate what that's going to do to my time, because right now I am sitting around 1.46 seconds average. So I'm like getting really close to the edge, and they keep going, yeah, we want to add this, we want to add this. You know, that's going to kick it over. Yeah, but we want it. You'll figure out a way. Oh, thanks. Right? So there's been times where we've had to design something and we test it. It takes too much time. We go back and redesign it because it wasn't fast enough. Right? So other examples of constraints are, it has to be done between 1 a.m. and 3 a.m. in the morning. That is the complete window that you have to do this in. That's not functionality, it's a constraint. You can only allow this many users into the system at any given point in time. Okay? Right. So again, that's not functionality driven, that is a constraint that you're adding into the system. So, do you understand what that non-functional analysis is about? So again, we've given you examples of those types of things, and then that maps into, from a database perspective, what do I have to do to fit within those constraints? Right? So it could be, right, I have one where every weekend, right, the system is unavailable online between midnight and 6 a.m. every Sunday morning. That is the point in time that I have to do all the database maintenance. So, any backups, any reorganizations, all that stuff, because otherwise, after that, when it comes back up, it's available all the way to the next Saturday night at midnight. So, all that monitoring I have to do, what do I have to do, when do I have to do things, right? So again, that's not a functionality, but it plays into the database scenarios of what we do and how we do it. Okay? So, if I was to wonderfully give you this picture and say, put in what's missing, you should be able to do that. Okay. So, any questions? Yes.
Why are the constraints not defined in the requirements collection and analysis part of the design process?
They are. There's a third arrow out of it. Right? So your requirements collection and analysis goes down data. It goes over here to functional requirements. So there should be a third arrow out here to non-functional analysis.
I have another question.
Oh,
There's no kind of validation, at least on this diagram, of any kind, and that seems like a mistake to me. Would we say that that's missing from a design as well?
what do you mean by that?
Feedback's the way it is.
Yeah, there's no feedback loop, validation, or verification of what you built. It just sort of, to me, looks like a jump straight to transaction implementation.
Well, their transaction implementation here is really a bad word. Right? Because this is, their transaction implementation is the actual building of the program, not implementation from a deployment perspective. But I would argue that I can't put a feedback loop on here. Because if I was to do what we just said earlier today, right, my requirements collection and analysis should be traced back for correctness to the problem statement. The conceptual design, the functional analysis, and the non-functional analysis should be traced back to the requirements collection and analysis step. The logical design, this data model mapping, should be traced back to the conceptual design, right? So each thing on here should be validated, in your term, to everything that's prior to that. So I can't put it on there because it's every single one of these. Right? So if you go back to when I was a database administrator and I created the physical design of the database in the database management system, before I actually created the internal schema and built it, I had to trace it back to the logical design that I came up with. And I had to make sure that the logical design I came up with matched back to the conceptual design that was given, and then map that back to what was provided to me by the business customer and the application team to say, right, this is what you told me. Did you guys make any changes? Oh, we changed it. Oh, I have to change mine. You didn't tell me about it. Thanks. Okay. So I'd find a whole bunch of stuff in that feedback loop, but that was all before I built it. But again, that is typically not what happens. We go through and just blast through, build it, and it's way farther into the process that we determine that we have a problem, and then we have to change everything all the way back. It's a huge effort. So we have this concept that we just talked about here of the cost of a change curve. What is the cost of every change? What's a curve look like? It's an exponential curve. What's an exponential curve look like? Right. Starts out small and ramps up and then goes exponentially high. Right? Right. So, if my x-axis and y-axis, so it's cost versus time, right? Okay. And what does time represent? The time from when you should have made the change. Right? So if we think about it, right, is Cooper is back there typing in his little reviews of whatever he's reviewing, and he misspells a word. Right? If he changes that word right then and there, it hasn't cost him very much time. Right? But he has now written it. He's half paying attention to me as he's doing it. So he mistypes it and he posts it out there. And he goes back and rereads and goes, oh, there. So now he has to open it up to edit it. He has to change it. He has to save it. That's more time than just backspacing to correct the work. Okay. So now he puts it out there and somebody else reads it, says, hey Cooper, you know, you like misspelled that out there, right? So now his image is ruined because, you know, somebody else has realized that he can't spell correctly or his typing skills are lacking, something like that, right? So he's taking, right? So we have a problem, right? So the same thing happens here, right? So what happens if I get the problem statement wrong? And before we do anything else, we review it and we correct the problem statement. You corrected a document, but everybody's in agreement and then you move on, right? Okay, so what happens if I'm creating my scenario models and it's based off of the wrong problem? But you realize after you do all of the scenarios and reviewing that you're doing the wrong problem. I go back and fix that, I update the impacted scenarios, and we're good to go. So it costs more, but not that much more, right? You created the problem statement, I now do the scenarios, and everybody agrees with those, and I'm into the conceptual design, and I get that wrong. Well, it was wrong because the requirements were wrong. So now I have to go back in, right? So I have to go back to different layers and I have different problems, right? So I have the conceptual design right, but I translated it into the wrong logical design. Right? If I'm in the logical design and I get the logical design wrong and I fix it before I move on, it's a small cost, right? So the axis of the X and Y axis is the point in time whatever change needs to happen. And the more things, the longer time it takes to find and correct it, the more things that you're going to have to do to fix it, so the higher the cost. And it applies to every change. That is the two documents that I go through with my business customer every time I get a new one assigned. cost of a change curve. Every time you tell me to make a change, this is the cost impact. The farther into a project you want me to make a change, I think, the farther in that we make a defect, that we have to go back, every time, there's a cost. You have to understand this. Right? The other thing is I walk them through the complete ERD, and almost every single time they go, I never realized that. We can do that? Really? We have that data? Right? People change jobs all the time, but the complete ERD representing your mini world doesn't change. So you coming in and say, what goes on in our organization? Look, here's all the data. Here's all the entities. Here's how they all relate to each other. Right? That's going to make it easier for every person that comes on, right? Every person that comes onto my team, that's the first thing I have them look at. They want to, what do you do? I don't care what we do. I want you to understand the data that we deal with. Then we'll worry about what we do with it. All right, so any questions on this? All right, so for our conceptual design, as I said, we deal with entity relationship diagrams. We have the enhanced entity relationship diagrams, right? We have design tools that help us out in designing and documenting all these different systems. And we have UML, which is the Unified Modeling Language that ties into the class diagrams that we do, right? And again, what do we know about class diagrams versus your databases? That classes should match in terms of the data. If I have a student class and I have a student database, the data should match, or I should have a reason why they don't. If I have a course database and I have a course class, they should match. If I have a building database and a building class, the data should match. Right? So, we want to create a database schema design based on the following requirements of the company database. So the company is organized into departments. Each department has a name, number, and employee who manages the department. We keep track of the start date of the department manager. The department may have several locations, and each department controls a number of projects. Each project has a unique name, unique number, and located at a single location. So, let's think about this. What are all the things? So, right? Company is kind of this overarching thing, right? So what are we modeling? We're modeling the company, right? We're modeling the university, right? University typically isn't the theme necessarily, right? Okay. So we have departments that, and we look at this, what else do we have?
Managers.
Well, we always have to have managers, but a manager is what?
That's an employee.
Employee, right? So we typically are not going to have a manager entity because every manager is an employee, right? So again, you're reading through this and going, wait, I have two things that are the same but called different things, right? So again, if you go to a company and you ask the same questions to multiple people, you will get multiple descriptions with different words that are meaning the same thing, right? So think of a airport. You people describe it, they will talk about planes. They will talk about aircraft, right? Are they the same? Yes, right? But they are, right? People will talk about it in different terms. And you, being the person that's in charge of all this, is going to have to decipher that they are the same. What could help you with that? starts with two D's.
Data dictionary.
Data dictionary, because I could have a definition that says aircraft, but I have an alias of airplane, a plane, or I can list all of them out so that whenever I looked up what they were, the whole thing would pop up, and then everybody is using, even though they're using different names, we all know what the same meaning is. Okay? Okay? So we have employee, department, and project, and we have whatever this magic location is. Okay? So, what have they done here? They've highlighted company, department, and project, but if you were really designing for this, you would have to cover employees and locations. Okay? So, you're reading through these descriptions that somebody is telling you. Right? Typically, nobody hands you this wonderful document and says, go read this because this has everything in it. You have to go talk to everybody and decipher all of this based on what they say, not what they have written down, which makes it even harder. Okay. So, our database is going to store for each employee their social security number, address, salary, sex, and birth date. Each employee works for one department, but may work on several projects. Nice. The database will keep track of the number of hours per week that an employee currently works on each project. Okay. It's required to keep track of the direct supervisor of each employee, which is different than the manager of the department. Okay. Okay. Each employee may have a number of dependents. For each dependent, the database keeps a record of name, sex, birth date, and relationship to the employee. Right? So again, now you're picking up all this other stuff. Right? Okay. Now, would it be easier if you already walked in and somebody had a complete diagram of all of this for you to start with, and they, as they're talking, you're just checking off, okay, they've mentioned this, they've mentioned this, they've mentioned this, right? As opposed to, oh, we don't have any document like this ever, so we're going to create a new one. Again. Right? All right, so we're picking out the things, we're picking up the attributes about those things, and what are the relationships. So, our ER model concepts, right? So entities and attributes. So entity is the basic concept because it's right in the title of entity relationship, right? So they are specific things. So even the book talks about in terms of a thing, right? So we are representing that in the database, right? My argument is I represent that in our complete diagram first. We decide what we're going to build, then it may or may not be in the database that we actually built. Okay. So, employee, John Smith, the research department, and the product X project that we're dealing with. Attributes are properties used to describe an entity. So, right, employee has the entity or attributes of name, social security number, address, sex, date of birth. We have values for each one of the attributes. So again, when we talk about the behavior or the state, this is the data that we actually have. Right? So John Smith has a specific social security number, a specific address, specific sex, and a specific birth date that we have associated with them. If any of that changes, we are changing their state or their behavior. Okay? So each value has a value set or type associated with it. So integer, string, date, right? Things like that, right? Okay. So where are you going to know what those are? The data dictionary, right? So if it's already been defined, or even if it hasn't been defined, but we know what it is, because we're not storing it, right? I can go to the data dictionary because the data dictionary doesn't represent just what we have built. It could be a term that the business uses. And we can say, okay, it's a date, or it's an integer, it's a real number, right? Okay? So it may be something we calculate. You're looking at a data dictionary as any term that you use anywhere in the organization, because if you want to know what something means, that's where you can go to find out. And like you said, a lot of times we give examples in there of what they are, things like that. Okay, so we have from a type of attributes, we have simple, composite, and multi-valued. Okay, so simple is we have atomic values for something, right? So social security number, sex, whatever, right? We know that it has a value and we're just good to go. Not to worry about. Okay, composite means that the attribute is composed of several components, right? So in our example here, we have address being apartment number, house number, street, city, state, zip code, country, name has first name, middle name, last name, right? So we could have a hierarchy. Now, this is where you start making decisions. Am I going to store it as a single composite or individually? Why is that important? If I'm going to be searching on things that are going to be reporting out by country or by zip code or by state, I'm probably going to want to not have to parse out those pieces of data every single time because it's going to take longer. So I'd probably have them as unique individual data fields. If I'm never going to do that, or at least currently I don't intend to, then I know what those are made up of, but I will store it as a combined. So we've had plenty of instances where we have made the wrong call and stored the combination as a composite, and then people want the individual pieces. We can't parse it fast enough, so we have to then go back and redesign and unload the database, pull out the pieces, put them back, right? Because we're making a change, right? So again, it was late change, higher cost. Okay, so multi-valued is an entity that has multiple values for that attribute. So color of a car, previous degrees of a student, right? Right? So for a given entity, right? So a one that you guys may or may not have is phone. Right? Some people have multiple phones. Okay. Okay. So in general, our composite and multi-valued attributes may be nested arbitrarily to any number of levels, as we talked about, right? So again, you could have previous degrees being multi-valued, but each one of those is made up of college year, degree, and field, right? So as we said, multiple previous degrees can exist, and each one has the 4 attributes associated with it. Okay, so if we were to draw out the hierarchy, we have address made up of those, right? So again, a lot of times we have drawings like this just to show how it lays out. All right. Okay, so entities with the same basic attributes are grouped or typed into an entity type, right? So our entity type are our groupings of things, right? Employee, project, student, course, department, right? So, right, we divide them up. So an attribute of the entity type for which each entity must have a unique value is called a key attribute. Right? So, social security number of an employee. Unique?
Hopefully.
Hopefully. But we have encountered multiple instances where it is not unique. And actually, because we actually, the customers have to supply us their social security number, we are actually somewhere around 5% multiple people having the same one. So, not a good, unique test. And one of my employees actually has 2 social security numbers. So not it's 2 different people having the same one, it's same person has 2. Okay, key attribute may be composite, right? So vehicle tag number of a key of a car is a key of the car entity type with its component, the number and the state, because the number may not be unique across all of these states, but the combination of that number and that particular state will be unique. Okay. An entity type can have more than 1 key, so the car entity type can have 2 keys. So we have the VIN number, or vehicle identification number, and the vehicle tag number, which is their license plate number. Right? So we have, in general, things that we call a primary key, which is the one that you're actually using to look at uniqueness. We have secondary keys, which are other keys that we use to look things up. And something like this, where we have 2 that are going to drive uniqueness, we say that those are candidate keys, because those are both candidates to become the primary, and you as the database designer is going to have to pick which one to use, because you only use one as the primary, everything else is secondary. Right? So each key is underlined, right? Okay. So, okay. Now we have different underlinings, which is what they don't get to. So, right, they indicate here that in a relational schema you have a primary key and it's underlined, which is true, and we stick to that. In general, the other keys that you have a dashed line underneath it, or some other indicator to say, I am using this as a way to look up data in this particular database. So again, there's different ways that we look at this, right? So we'll talk about some of those, but again, I just want to point out that there's different things, because it's, of course, not standardized across the way that we do things, because who'd want that? Right? Okay, so the entity set is, right, and for each entity type, we have a collection of entities stored in the database, right? Okay, the previous slide showed the 3 car entity instances, the same car used to reference both the entity type and the entity set, right? So I get hung up in all these words, right? So the thing I want you to remember is we are modeling entities because we have a entity relationship diagram. So we are interested in the entities. We want to know how to uniquely identify a piece of data or an instance in the database. I want to know, if I'm going to build this, I need to understand what are all the possible ways I'm going to be searching for data in the database. Because that's going to drive how I build it. The complete set of values that you have in the database, we are going to be calling the domain of values. What that means is if I go to the student database and I type in a student number, because that's unique, if it's there, that is the one and only instance associated of that number. So that's the student. If it's not there, there is no student in existence anywhere at any point in time that has that number. Because if I look it up, the student database has all of the students. Now, we can argue about current students, right, versus students that aren't currently attending, all that, and you can divide that all kind of, so you can make arguments. But the point is that if I'm creating a database, that population of all the data and all the instances out there for that particular database is, if it's there, it exists. If it's not there, it doesn't. And so that's the domain of values. Yes, sir.
Can a domain have multiple entity types?
What do you mean?
Can there be entities representing people and entities representing buildings in the same database? Is that all part of the same domain, or do they have their own
No,
separate domains?
no, each set, so in your instance, the domain of values that we have in the student database is all gonna be based off of student number. The domain of all of the buildings is based off of the building code. PEC. I find it. It's right here. The XYZ building, I don't find it because it doesn't exist. It's not in the domain of the buildings, because it doesn't exist in the database of buildings.
So domains are restricted to one entity type.
Yes,
Thank you.
you are welcome. And with that, have a great night.